Welcome to lecture 6 of Embedded Systems, in which we shall discuss finite state machines and their implementation in the ARM cortex-m microcontroller systems. Finite state machines can be described by the set of inputs, outputs, states, and transitions. And all of that can be described in the form of a state graph defining the input-output relationship. Let me give you an example of a finite state machine that you're already familiar with. This is an example of a JK flip-flop. In a JK flip-flop, the output of the flip-flop can be either 0 or 1. And we know how to transition from the output state 0 to 1. And that can be inferred from the truth table. For instance, we can put j equals to 0 and k equals to 1. So j equals to 0, k equals to, sorry, this is the opposite. So going from 0 to 1, meaning that we would like to put j equals to 1 and k equals to 0. Likewise, if we want to transition from the output 1 to output 0, that means j needs to be 0 and k equals to 1. That is a reset state. And if we wish to retain the output same as the one in the previous clock cycle, then we would like to have j is equal to 0, k equals to 0. Same here, j is equal to 0, k equals to 0. And finally, if we want to toggle, then the j equals to 1 and k equals to 1. Toggle 1 to 0, j equals to 1, k equals to 1. So this is a quick example illustrating the basic components of the finite state machine, and in this case you can consider j and k as the inputs to the system, inputs, and the q over here, the q next, q, and as indicated here, is the output, and coincidentally q is also the state, because this is representing the memory component of the JK flip-flop. And these arcs represent the transition that we described earlier. And this is a pictorial representation of a finite state machine. Let us summarize the essential elements of the finite state machine. The most important one being the state. So we looked at an example of a JK flip-flop, and essentially the state is a description of current condition. In case of JK flip-flop, the current condition was the output of the JK flip-flop. And an interesting attribute of the output of the flip-flop is the presence of memory. Is something that can be stored or retained. Quite naturally, in the digital world, when we talk about the state, it is usually a case that we are trying to describe the current condition in a binary form, such as 0 or 1. However, remember that state is not only specific to the digital system, and you can find examples of the state describing the analog system, such as the voltage across the capacitor, VC, that's capacitor voltage, is an analog quantity because the capacitor can store charge in terms of voltage. Likewise, the inductor current is also an example of a state, although it's not a digital state, it's an analog state, because inductor stores magnetic field that is proportional to the current. The graph state is essentially an interconnection. The state graph is actually an interconnection between the states, as we saw in the previous example, when the transition was required from JK output state 1 to JK output state 0. In other words, these arcs between the two states representing the output of the JK flip-flop, these arcs along with these states and also some other transitions corresponding to the retention of the states, as well as the labels of these arcs, such as the values of J and K, all of that represent a graph known as the state graph. So the question is, where does the controller fit in the paradigm of the finite state machine? And in fact, in this lecture, we're going to study how to program microcontroller to run a state machine or to implement a state machine. In fact, whatever dynamics are associated with the state machine, those are controlled by the software. That is, the changes in the inputs and the output, as well as the state and the accesses to the state graph. So whatever is happening, whatever makes the state transition, whatever makes a system to change the input, whether it is coming from the external peripherals, and the microprocessor is responsible for inputting those inputs to the system, and then whatever is responsible for changing the output and hence the state, all of those tasks are accomplished by the microcontroller. So we are going to understand the concept of the finite state machine with the help of an example in this lecture. In mechatronic engineering, the finite state machine has a special structure. The inputs are usually coming from the sensors in the system, and the output are usually attached to the actuators. For example, the input may be coming from the temperature sensor, and the output may be controlling the fan motor, responsible for controlling the speed and to be able to change or adjust the speed. And who is going to do all of that? Who is going to accept the input? That's the controller. And who is going to change the output? That's the controller. And how does it do that? It does it with the help of the realization of the state graph as shown here. This state graph contains 4 states, and these states are representative of a traffic control system. It's a bit more complex than the state diagram of the JK flip-flop. So we shall understand the implementation of the traffic light control system and how we can attach the sensors and the actuators to the controller, and how we can program the controller to implement the state machine. The 2 most commonly used types of finite state machines are the Moore state machine and the Mealy state machine. Essentially, we are going to describe the difference between the two by noting the difference between the state and the transition. So in case of the Moore state, the output is a function of the state only. So output depends only on the state. So the output depends only on the state. So in that sense, if the state is known, then we can readily tell the output. Whereas in case of melee state machine or the melee state, the output depends also on the input. So in this case, you see the output has been drawn on the arc, and arc is associated with the input. So this transition is represented by an arc, and that occurs when the input is 1 over here, and it gives you an output 1, 2, 3. But in a sense, the output also depends on the state, because this arc is coming out of a state. So we can say that in the melee finite state machine, or the melee state, the output depends on the state as well as on the input. And except for this difference, there is no difference between the two states of the two finite state machines. In this lecture and also in this course, we are going to restrict our attention to the Moore state machine. The defining characteristic of the Moore state machine has been already described. Let me give you a quick recap. In the Moore's finite state machine, the output value depends only on the current state. That is, the output completely defines the current state completely defines the output. And the role of the input is to enable the transition, that is, when to change the state. For a given Moore finite state machine, there are following steps that are required to implement the state machine. For any given state, perform the output action corresponding to that state. And once the output action has been performed or the output has been generated, then we often want the microcontroller to wait for prescribed amount of time. However, note that this wait time may be optional. Nevertheless, the next step is to read the inputs. And after the inputs are read into the microcontroller, we apply the state change if required. That depends on the input and the current state. In fact, what we're saying here is that the next state depends on the input, the current input, and the current state. And once the state transition has occurred, that is, we have moved on, the microcontroller has changed the state, then we repeat the whole process or go back to step 1 and start over. And this process continues forever. Essentially, that's how we implement the finite state machine, except when we want our microcontroller to give the control back to the operating system. Otherwise, we would like microcontroller to keep jumping from one state to another and repeating these 5 steps over and over again. How to implement a finite state machine, and what is the appropriate data structure? There can be many options. It can be that the state machine requires multiple identically structured nodes, or it can be statically allocated fixed size link structure, one-to-one mapping finite state machine graph and the link structure, and one structure for each node. So we can think about this type of implementation as a form of a linked list that is essentially consisting of identically structured nodes and statically allocated fixed size linked These data structures are linked, and each node is identically structured. There can be other types of data structures for the implementation. For instance, we can use pointers. That is the linked list implemented in the form of a pointers, the arcs connecting the nodes. And we can also use tables. But as far as our discussion is concerned, we're going to stick with the linked list and the pointer implementation. Let us now look at a real-life example of the implementation of a finite state machine. In this example, we are interested in controlling a traffic light system, and we are going to use our ARM cortex-m4 microcontroller, LM3S, or in our case TM4C series microcontroller are more relevant. There are two inputs, 2-bit input to the system, to the microcontroller. Those are available at the first two pins, or the two least significant bits of port E, describing the inputs. These inputs are coming from the sensors that are installed as part of the traffic light control systems. One sensor is indicating the presence of traffic in the north direction, and we are assuming that the output of the sensor has been digitized so that the output of the sensor can either be 0 or 1, where 0 indicates no traffic or no cars in the north lane or the north street or the north direction, whatever is the interpretation. So no car here in the north direction, and 1 means that there are some cars in this north direction. So there might be some cars in the queue or on the north side of the traffic signal. So 0 means no traffic, no car, and 1 means there are cars. Now, same goes for the traffic in the east lane or in the east street or in the east direction. That information is again digitized 0 or 1, available at pin number 0 of port E. So when the two-bit inputs are taken together, then there can be 4 options. 0, 0, meaning no cars exist on either road. 0, 1 means that there are cars on the east road, on the east street, but there is no car on the north side. 1, 0, the opposite. There are cars on the north road and no car on the east. 1, 1 means the cars on the both roads. It is important to note that these 2-bit information, that this 2-bit information comprises the input to the microcontroller. Once the inputs are defined, we now proceed to define the outputs and the states. Those are available at port B of the microcontroller. So port B is associated with the output or the state, because the output can be completely specified by the state. In fact, the arrow should be in the other direction, and this should really be the state. So once the state is known, then you can readily tell the output. So therefore, the port B is associated with the state or associated with the output. Now in this case, the output should be able to control the traffic light. 3 of the port B outputs are controlling the traffic signal for the traffic or the cars on the east road, and the other 3 pins on the other 3 bits of port B specify this traffic control signal for the cars or the traffic on the north road. So with that configuration, our job is to define the role of each bit, or the set of 3 bits. So essentially we have divided the whole ports into a set of 3 bits each. The lower 3 bits control the traffic signal for the traffic on one of the roads, and the upper 3 bits control the traffic light for the cars on the other road. For instance, if we look at what kind of signals are required to make sure that we give a go north signal, so GON, go north, giving a green signal to the traffic on the north road. For that to happen, we would like to put 1. That will turn on the green light. And when the green light is turned on, then naturally the yellow light should be turned off, and so is the red light on the same traffic signal. So this gives us 0, 0, 1 on the three least significant bits of port B. And when we assert the go north signal, then we are really making sure that there's a traffic in this direction. But we don't want any traffic in the east direction. That's not allowed. Therefore, we want to put the red signal on here, 1, 0, 0, 1, 0, 0. So this makes the 6 bits. We are working with the 6 bits of port B, or the 6 pins of the port B. 1, 0, 0, 0, 0, 1 makes it green on the north and red on the east. That constitutes the go north signal. Later we are going to call this a state. I'm going to call this a state. So what we have understood so far is that go north is one of the states, or you can also say it's one of the outputs of the system. We can also define another state, which is the opposite to the go north state, or the go north output. This output is go east. And it occurs by turning the red signal for the north traffic and green signal for the east traffic. And for that, it can easily be seen that the output needs to change. So the red signal over here and the green signal over here, which means that PB2 should be 1 and PB3 should be 1. And all other bits should be 0. That makes it 0, 0, 1, 1, 0, 0. That is another state, go east. Another state, another output, go east. There can be other states as well. For example, there can be a state or the output, wait north, in which we really want the green traffic to prepare to stop. So considering that there was this traffic flow here in this direction, but now we wish to stop the flow or stem the flow. But that cannot occur instantaneously. If there was a traffic in the north direction, that this bit must be 0, the yellow must be 0, red must be 0. So if we want to make a transition from let's say go north to go east, this transition cannot occur instantaneously. There must be an intermediate stage, or that is actually this wait n. That occurs when we put a yellow signal on and green signal is turned off. So now we are in a different state, wait n. And when we turn on the yellow light for the north traffic, then the we still want the east traffic not to move, so we still want the red light on for the east traffic. Hence 1 0 0 0 1 0. That corresponds to the wait north. So so this wait end state is important. It acts as a transition from go north, wait north, and then go east. And this is the sequence that we have understood. And it is the sequence that is consistent with the real life observation and implementation. But there is another state when we go from the go east state to the go north state. And that cannot be done instantaneously. Therefore, to understand this transition, if we are in the go east state, that means the green light is 1 for the east traffic, yellow is 0, red is 0. And the red is 1, yellow is 0, and green is 0 for the north traffic. Now, if we want to stop, if we want to signal the east traffic to prepare for a stop, then we want to go from 001 to 010. And then the signal on the north traffic is still the red signal. This makes it 010 100. This corresponds to the wait E state. That is, we are signaling the east traffic to prepare for a stop or to wait. Therefore, from go E, we go to wait E, and then we go from wait E to go north. The complete state transition diagram will be shown in the next slide, but I hope that that clarifies the significance of the state, the 4 states that we have defined, and how we can possibly transition between the states. Quite naturally, the transition must be powered by the inputs. So to summarize, these are the inputs. The inputs are available on the port E, the 2 least significant bits of port E. And the outputs are available at the least significant, the first 6 bits of port B. You can consider them as the outputs or the states. Because in case of the Moore finite state machine, the output is completely dependent on the state. So in this case, we have a luxury of a one-to-one relationship between the output and the state. Now we construct this finite state machine graph, state graph. Over here, it is shown by means of 4 states: go north, go east, wait east, and wait north. There are 4 states, and there's a transition shown by means of the arcs. Now, to understand each state is specified by its name, that is go north. So that is essentially the name of the state. Name of the state. It can be go north, it can be wait N, it can be go east, or it can be wait E. So the first of the 3 items indicated inside the circle represents the name of the state. Once the name is specified, then we have to give the output associated with the state. So the next item indicated in the state circle is the output. So when the system is in go north state, the output is 10001. What that means is that if I say that my output is 1001, it means that I am asserting the red signal for the east traffic and the green signal for the north traffic. So that's why it's 100001 over here. That is the output, and the microcontroller in the embedded system implementation, the microcontroller will output this 6-bit number on port B to turn to control the traffic lights. That's the problem that we're trying to solve, and it is the output 6-bit number that is outputted from the microcontroller. So the output is also shown. It's a second component that is indicated in the state circle, and then third component is the wait time. So in our case, this specification requires that the green or the red light will stay on for 30 units of time, maybe 30. We can just simplify that. Let's say 30 seconds. So the green or the red light, whenever is turned on, it stays on for 30 seconds, and it lets the traffic, the corresponding traffic, to flow for 30 seconds. Whereas the wait, which corresponds to the yellow light, stays on for 5 seconds. Therefore, the wait time for the go north state is 30 seconds. Likewise, the go east state is also 30 seconds, meaning that once you enter the go north state or the go east state, you stay in that state for 30 seconds. In other words, if you enter one of these go north or the go east state, so let's say we enter this state, we stay in this state for 30 seconds before transitioning to the next state, which is wait end state in both cases. The wait time for the wait end state is 5 seconds. Wait east state is 5 seconds. That north or east, both cases, this is 5 seconds. But what about the inputs that are going to bring the state transition? We have a 2-bit input, PE0 and PE1. These are available at the least significant bits of port E. So let's consider an example. We are in the go north state, and which means that we are really allowing this traffic to pass, go north. Now we want, now we sense the input. So for example, if there is an input 0, 1, what this means is that the traffic to the north has ended. The traffic on the north road has ended. So traffic in the north has reduced to 0. And 1 means we have traffic in east. It means that all the traffic from the north has passed. There's no cars here, and there are lots of cars here. There are some cars, so cars. In that case, we should start preparing to turn off the green light for the north traffic, and so to go from 001 to 010. This is the idea. So in other words, we really want to go from 10001 to 10010. So we are going to go from green light for the north traffic to the yellow light for the north traffic, and that is essentially wait N. We are putting the traffic on the north road to come to an halt. And if we have input 1 1 in both, again, if the input is 1 1, we have a traffic that has not finished. We still have some traffic. That is, we have cars on the north and we have cars on the east. 1 1. So traffic in both directions, but because we have already allowed access to the north traffic or the cars on the north, and we cannot keep waiting the cars on the east, we have to perform the transition nevertheless. So in both cases, we allow this transition. So from go north, spend 30 seconds, and then essentially, if we have some cars on the east, whenever we have some cars on the east, regardless of we have cars or no cars on the north, regardless, we are going to make a transition. We are going to change the traffic signal. If, however, there is a situation, if, however, there is a situation that there is no car on the east, no car, and the green signal is on for the north, then we stay in the same state. We're going to stay in the same state. So as long as there is no car in the east, we remain in the state. But as soon as there is a car in the east, then we begin to make a transition. This is what it means by 0, 1 and 1, 1. So depending upon the sensor output, which is sensing the traffic in the north and the east road, we make the state transition. Either we retain the state or we go to the next state. All right. I hope this makes a lot of sense to you. So once in the wait n state, then regardless of the input, we wait in that state for 5 seconds. Then whatever is the input, car, no car in the east, car or no car in the north, that is traffic, no traffic, regardless, we are going to make a transition from wait n to go e. So whatever is the input, make a transition, whatever is the input. So we can say whatever is the input. Actually, in this case, input doesn't matter. Whatever is the input, make a transition, and the next state will be go east. Let me quickly remove this text over here. All right, almost done. So once in the go east, meaning that in the go east, we arrive in the go east state by asserting an output signal which is 0, 0, 1, 1, 0, 0, 1, 1, 0, 0. The output in this case is 0, 0, 1, 1, 0. What that means is that the green signal is turned on for east traffic, and the red signal is turned on for the north traffic. And in this case, we shall wait for 30 seconds before making a decision on the transition. So one of the things to note over here is to wait for 30 seconds before making a transition. That is, before changing the light signal, and by change, so that's why the most appropriate word is the transition. So if you want to think about the change in the state, that change may actually bring you leave us in the same state or in the different state. So that's why this transition. The transition doesn't necessarily mean go from one state to a different state. It can actually mean also to remain in the same state. So you have to wait for 30 seconds before making a transition. That is, before reading the next sensor input. This is what it means. All right, so here we say that if there is a car on the north, then we shall make this transition after 30 seconds. And if there is no car on the north, then we shall remain in the same state. So if we have to make a transition, then we go to wait E, again wait for 5 minutes, and then whatever is the input, we go to the go north state. And this is how this traffic light control signal will continue to run. According to this diagram, it will continue to run indefinitely. We can also represent the finite state machine diagram constructed in the previous slide in the form of a table. So the table has 4 rows corresponding to the 4 states. These are the 4 states, and each state is specified by the output and the wait time. So for go n, we know that the output was 100001 and the wait time was 30 seconds. Then corresponding to each, the first element of each row, we have 4 columns corresponding to the 4 inputs 0001, 1011. So from go north, you can go to the same state, go north, when the input is 00, and you can go to the go north state when the input is 10. That is when we have no traffic on the east. However, if there is some traffic on the east, if there is some cars or one car, depending upon the interpretation of the signal, then we go to the next state, which is we go to a different state, which is wait n. So this is so if you are in the go north state, then depending upon the inputs, the next state is written here in the same row. Same goes for wait n, but in case of wait n, you necessarily transition to the go east state regardless of the input. So the input really doesn't matter in this case, but for the sake of consistency, we say that whether the input is 00, 11, 10, and 11, the next state of wait n is always going to be go e. But then if you are in the go e state, then we can go to the wait e state if there are cars on the north road over here. But we keep on this. We keep the same state. We do not make a we do not go to a different state. We stay in the same state if there are no cars on the north, 0, 0. And finally, the wait e state necessarily go to go n regardless of the input. So this table is equivalent to the state machine diagram or the state graph that we drew on the previous slide. The first step to program the microcontroller for the implementation of the finite state machine is to encode the state machine in the microprocessor memory, ROM in this case. Why ROM? Because once encoded, the finite state machine information is not going to change. And what are those pieces of information? The output, the wait time, and where can we go from one state to another, the neighboring states. So if we look at an example, from where can we go from the go north or go n state? We can stay in the same state, go north, or we can go to the wait n states, go n or wait n. So there are 4 possibilities. Therefore, in order to encode the state machine, we can translate each row of the table constructed in the previous slide as follows. For each row, we provide the name of the state, go n, and it is stored in the microprocessor ROM as an array whose precision is 32 bits. It's an array whose precision is 32 bits. Therefore, we make use of the assembler directive define constant data. Define constant data. We have used this assembler directive for all the states to be encoded. DCD, define constant data. The first element of the array is the output corresponding to that state, and that has been converted from binary to the hexadecimal. You can verify that from the previous slides. The wait time in seconds, and then the sequence in which the new states can be reached from the current state. Again, see the table, the last slide. In fact, we have replicated the order in which the states appeared over here, and these are going to go into the ROM. The second row of the table corresponds to the wait n state, whose output is hex 22. Delay is 500, corresponding to the 5 second. Later on, we shall make more sense of these numbers. Why 3000 corresponds to 30 seconds is the factor of 10 here. And then we have the sequence in which the neighboring states can be reached. Essentially, if you have forgotten, then this corresponds to the input 0, 0, 0, 1, 1, 0, 1, 1, and the same goes here 0, 0, 0, 1, 1, 0, and 1, 1, meaning that if you're in go n state and if the input is 0, 0, then you stay in the same state. But if the input is 0, 1, we go to the wait n state, and so on. So this sequence corresponds to the inputs 0, 0, 0, 1, 1, 0, 1, 1. Again, for detailed discussion, see the last two slides. So all of these are in total 4 arrays. These are in total 4 arrays, each containing 1, 2, 3, 4, 5, 6 numbers, 6 32 bits number. So in total we have 4 arrays, each containing 6 32 bits number, and therefore overall 24 numbers, each with 32 bit precision. To understand this in more detail, let's proceed. The actual map of the go n state array, if visualized, how is it going to be stored in the ROM, then on the right hand side I have indicated the ROM data, and on the left hand side I have indicated the ROM addresses. So there are 6 elements in this array whose label is go n. Essentially, this go n is representing the base address of this array. If you add 4 to the base address, you are indexing the second element, or element and index number 1. So let me write down the indices here. Index number 5, 4, 3, 2, 1, 0. And over here, if you match these indices with the offset, so whatever is written after plus in the address section, these are the offsets. So hex 21 is at index 0. It is locating exactly at the base address of go n, and hex 21 represents the output. Remember, It is the output. The next index contains the wait time data 3000. That is at index number 1. But the address is base address plus 4. So the offset is 4. So here is the offset. So all of these are offset. And remember, the address, the total address of any element is the base address plus the offset. And offset, this offset is n times I from our last lecture, where I represents the index. It's the same I representing the index. And n is equal to 4 because the precision is 32 bits. Therefore, we can calculate the complete address of any of these elements of the array of GoN. Later, we shall use these base plus offset technique to compute the total address, the complete address of any element of the GoN when we wish to access the output or the wait time, or where do we go to, or the address of the next state. One of the important things to note over here is the meaning of the DCD corresponding to the definitions in the third row. So when we say DCD GoN, remember GoN is just GoN is a label. So when we say GoN, it really means, essentially it means that we are storing the base address of GoN because this is a label. Remember, it is a label, and label always means an address. Wait n is also a label, GoN is also a label, so is wait n, and label means address. So in other words, when we are going to store these labels in the array, we are essentially storing their base addresses. Wait n base address, GoN base address, wait n base address. And we can think about the visualization of GoE and wait E and wait n, all of these arrays, in the next few slides. The GoE array is stored in the ROM in the same way. Index 0 contains the output, index 1 contains the wait time number, and the last 4 indices correspond to the base addresses of the states GoE and wait E. Wait n as well as wait E arrays are stored in the ROM as shown here. All these 4 arrays are stored in the ROM. This is how you may want to visualize them. An interesting feature of structuring our arrays in the ROM is that it immensely simplifies the state transition process. For instance, if we go from one state to another depending upon the input, for example, if we go from GoE state to the wait E state, then depending upon the input, we can readily we have the wait E state base address readily available over here in this array, which can lead us to the wait E array contents. And once there, we can output hex 14 and then the wait, send an instruction to the microcontroller to wait for 5 seconds. And then from wait E, if we have to make a transition once the 5 seconds are over, then we have the address of the next state, GoN, readily available, and we can make a transition over here. And once in the GoN state, we can output hex to 1, then wait for 30 seconds, and then if a transition has to be made, in this case, wait n state, then the address is already computed, it is already available in the array, and from there we can go to the wait n array and then continue from there on. So to summarize, this is how we are going to store our data representing the finite state machine. In writing an assembly language program, some constant will be used in addition to the data of finite state machine. These are constants 0, 4, 8. We could have done without them as well, but it just makes your assembly language program easier to write and comprehend and looks pretty tidy. Once the state machine has been encoded in the microprocessor ROM, we can then proceed to write the assembly language program. However, note the code that I'm going to describe here assumes that the port E and B base addresses are also stored in the ROM with the name sensor that corresponds to port E. So sensor will carry the base address of port E, and light carries the base address of port B. These are also defined and stored in the ROM. And it is also assumed that we have a code written already for the port B and E initialization as well as the initialization of the timer. Then the main part of the code goes as follows. We're going to load the base address of GoN state, assuming that this is the initial state. We have to assume some initial state of our system. Let's say initially we were allowing the traffic on the north lane to proceed, blocking the traffic on the east road. So the base address of the GoN array goes into R4, and the base address of port E goes into R5. Base address of light E goes into R6. Then, in order to understand the code, I'm giving an example of how one of the arrays can be GoN array or GoE, wait N or wait E, whatever that is, that's stored in the memory, and it contains 6 elements, and each element has a unique index, 0, 1, 2, 3, 4, 5, and the corresponding offset addresses. All of these were shown in the previous slides. Alright, so the first step is that once we are in a given state, then the first thing we need to do is to produce the output. We have to produce the output. And the output is stored where? It is stored at index number 0, and offset address is also 0. So remember, the total address is the sum of base address plus n into I, where I is just the index and n is equal to 4. So essentially this is 4 times index because our precision is 32 bits. So base address of the state array, base address of, in this case, the base address of GoN. So this is how the address is going to be computed. So therefore there is a one-to-one correspondence between the index and the offset. Essentially, if you multiply index by 4, you get the offset address. So with that in mind, the out, as defined as a constant, that is 0. This is a constant 0. So you just add 0 to the GoN base address, which leads you over here, the output, and you read. So the total address over here is the base address plus 0, right? So this out is representing an offset. It is an offset. If the offset is 0, we are essentially going to load the output into register R0. So by the end of this instruction, register R0 contains the output of go north, whatever that number was. All right. So the output has been stored in the register R0, and we are going to store that output. We're going to dispatch that output to the address stored in R6. And R6 contains the address of light, that is port B. So we are going to send the output to port B. So alternatively, you can say that send the output of GoN to port B. Or you can just say output value set lights. So once the output has been dispatched, then the next task is to wait. And the wait information, how long that you need to wait, is stored at offset 4 or index number 1. So offset, we're going to work directly with the offset here. So wait is a constant defined as 4. This is representing the offset. We're going to add to the base address of GoN. We're going to add 4 to the base address of the GoN, which is stored in R4. And we go there, and so this, by the way, this wait is different. This is the wait information, and we are going to store this in R0. So R0 now contains the information of the delay, how much delay that we want our microprocessor to produce. And then, if you remember, in the last lecture, we developed a routine, sysdig wait 10 milliseconds, which accepts input from R0, which makes your microcontroller to wait for R0 times 10 millisecond. Last lecture. So now we are going to wait. We are going to wait in the GoN state. And once the delay is completed, then our next task is to select one of these 4 indices depending upon the input. So are we going to select 2, 3, 4, 5? Which index is a question. It depends on the input. So from where are we going to get the input? The input is in port E. So now the input has been input address. The input port address, port E, is in R5. So we're going to index R5 to read the input. We are now going to concentrate in this region. Then depending upon the input, we are going to select one of these. So this corresponds to 0, 0, 0, 1, 1, 0, and 1, 1. It depends what input is available on port E. It depends. Whatever input is available on port E, we're going to shift it with 2. And the reason is that this input is a 2-bit number. It's a 2-bit number. And if you convert this into decimal, this will be 0, 1, 2, and 3. And this corresponds to the indices also. But these are not, this is not an exact match. In fact, we have to add something to these indices, which is 2. So the best way to do this is follows. We, instead of working with indices, we work with the offset. So read input and convert the input into the offset. We're going to work with the offset. So we know that the indices correspond to the offset when we multiply them by 4. So if, for example, we have, let's say, 0, 1. If we apply logical shift left to 0, 1, what do we get? Logical shift left R0, R0, hash 2. This is going to give us 0, 1, 0, 0, 4, which is 4. So this is a multiplication. If we have 1, 0, then this is 1, 0, 0, which is 8. And likewise, if this is 1, 1, it's going to give us 1, 1, 0, 0, which is 12. Therefore, we are going to convert the input into the offset. How? By applying a logical shift left by 2 units. And then add 8 to it. And this is going to give us the exact offset. So if, for example, the port E last 2 bits were 0, 0, you apply logical shift left, get 0, 0, 0, 0, and then you add 8. This is going to give you 8. And that is going to bring us over here. So from there we can read the address of the next state and then proceed therefrom. If it had been 0, 1, it would have given us 0, 1, 0, 0, add 8. This is going to give us a new offset, 12. And in that case, we would have picked a different address possibly, which is available at offset number 12. If it had been 1, 0, logical shift left, it would have given us 8. 8 plus 8, 16. 1, 0, 0. Here, we would have chosen this address, and so on. So this is how the input is directly converted into the offset. So logical shift plus 8. The next has been defined in the ROM as a constant 8. You can see from the previous slide. And once the address has been calculated as follows, then we are just going to add that offset. So at this point, maybe I should take some notes here. So at this point, remember, the important thing to understand over here is that at this point, R0 contains the offset address. And then to calculate the complete address, you need to add base to the offset. Therefore, base plus offset. That is going to give us the complete address. Where is the base? The base address is in R4. The offset is in R0. So so this should be this. Base is in R4 and it is in R0. There you go. And so you're going to load the data from the complete address, which is base plus offset, and that data is going to be stored in R4 register, load register R4. This means that now we have a new address. This is a new address corresponding to new address That means new state. I apologize for some delay in writing. Fully we can access. So new address means new state. So next time, so remember that our finite state machine must not stop here. Now we have loaded R4 with a new address. We must make a jump, branch, unconditional branch to finite state machine, means that we run and we iterate. And this time we have R4 containing new address for the new state. We go to that array and then start over and continue to repeat the process, and the finite state machine will continue in this way. Let us now discuss how to write the same program in the C language. We're going to make use of the struct as a constant, meaning that it is not going to be modified. And that is fairly consistent with the finite state machine description we provided in the assembly language code when we put the FSM information in the ROM. That's not going to be modified. It's read only. For read only purposes, we can make use of the constant struct. The name of this struct is state, and it has three attributes: the out, time, and the next. Next is actually an array of 4 elements. So this completes the definition of the struct. In our C program, we shall also use some constant, and they're the constant 0, 1, 2, 3, corresponding to the states of the state machine. We make use of the preprocessor directive define, which says that this constant 0 and this GoN, these are aliases. These are aliases, meaning that if we say 0 or GoN, these are synonymous. This can be used synonymously. Likewise, weight n is an alias. Weight n and 1 are aliases, meaning that if I write weight n, it actually means 1. If I write go e, this actually means 2, and weight e means 3. And all of these are defined with the help of preprocessor directive, that is define, #define. We can also live without defining these aliases of the constants. We can just write down 0, 1, and 3 wherever required, but this makes a programming task tidy and more reader friendly. Then we initialize. The next part is the initialization of the struct. So initialization is here. We are going to define 4 states. These are 4 states, and each state, so we have defined, so let me first erase some stuff over here. We have 4 states, and each state is of type struct, whose name is state. So each state is of type state. So in order to avoid confusion, we have defined an array of states known as FSM. So FSM is an array of states. It is an array of state. It's an array. The first array consists of three elements. One of them is the output, hex 21. The second is the weight. The third is an array, which actually defines the next possible state. So we know that the first state corresponds to the first state of this array in an order described in the table a few slides ago was GoN. And then the next state was weight N. Then the next one was GoE, and then weight E. So these GoN, weight N, GoN, weight N are the neighboring states, so states from where we can go after waiting in the state GoN. Again, consulting the table, we always go from weight N to GoE states in the same order. The third state is the GoE state, output, weight, and the neighboring states. And the final one corresponds to the weight E state. And the syntax of the structure is such that these three attributes should be represented in the parentheses. And the array, the third element, is itself an array, because this FSM is an array of state. So all the elements of an array should be provided in the parentheses. So but the important thing to note is that so this outer bracket corresponds to the array called FSM, and then each element is a state. Each element of this array is a state, and state is a struct of type struct, and we specify their values out, time, and x4 in parentheses. This is the important thing to understand, that both the array and the values of the attributes of the struct are defined inside the parentheses. Now, before we proceed, we need to define few more constants, input and light. And recall that input is available at port E, and the output, light, signal, is available at, or needs to be sent to, port P. Here we are trying to define input synonymously with port E data register. That is, input, in fact we could say that input has been assigned the port E data register, and more formally we could say that this is also GPIO port E data register. Likewise, light, we want light to be equal to GPIO port B data register. Now, in order to do that, we need to specify the address, or where can we find the contents of port E data register. Those are available at the memory address hex 400-2434C. In other words, port E data register is available at this address. Likewise, port B data register is available at this address. We know the address, but we don't know how to access the contents of the data registers available at those addresses. In order to accomplish this task, we utilize a special typecasting and a combination of typecasting and dereferencing the pointer. And we shall try to understand that in a step-by-step manner. Nevertheless, once these definitions are processed, then the thing to note is that the input becomes synonymous with the port E data register, and the light becomes synonymous with the port B data register. Now, as a part of your homework exercise, you're required to redefine the inputs and the outputs using bit-specific addressing, noting that we don't want to access the data of the whole port. In fact, we just want to access bit 0 and 1 of port E and bit 0 through bit 6 on port B. So therefore, these addresses which are representing the base address of port E, and this is the base address of the port B, these are going to be changed in the definition. Everything else will remain the same. Let us try to parse the pre-processing command beginning with define in the previous slide. If, for example, we define port E equals to some numbers, a 32-bit number here, hex 400243FC, we are really asking the compiler to place this number at some address, for example, address 2, inside the ROM, the read-only memory. However, if we modify the command by adding a typecasting operator over here, this really means that we are making port E as a pointer to an unsigned 32-bit integer. So remember, after inserting uint 32_t, we are making port E as a pointer to an unsigned 32-bit number. So the question is, what is the role of the uint 32_t steric? This is in fact a typecasting operator. We are converting this value as a value of a pointer. In other words, this number is no longer an ordinary number. It is the value of a pointer. Therefore, port E has now become a pointer. It is pointing, and it's shown here with the help of a green arc. It is pointing to an address hex 400243FC, and this is an address of the RAM. Now going further, once the port E has become a pointer, we could work with a pointer in our C program. However, it would be much easier if we work with the value of the pointer. Therefore, to convert port E back to a normal variable rather than a pointer, we apply the dereferencing operator. So in C, the steric to the left of this definition is performing as the dereferencing operator. What this means is that you revert port E to a normal variable, and in this case the normal variable means the value to which port E was previously pointing to. That is here. So remember, the normal variable are the contents of the memory, ROM or RAM, and these are different from the pointer, which we usually represent by means of arrows. So port E is no longer an arrow, it is representing the contents of the RAM at an address shown here. So port E is now at the end of this command, at the end of all this hassle, port E is the same as port GPIO port E data register. And now we can write data to the port E data register. We can read data from the port E data register simply by referencing this port E variable. So with that, we can reference port E data register using the word port E. And what happens, for example, if we want to read data, if we are reading data from port E, then a copy of data is stored. A copy is stored in the RAM. A copy is stored in the RAM. And next time, in the next read, it is possible that the microprocessor may just read the copy of a data which is already available in the RAM and then process that. And the actual data on port E may be changed. So therein lies the danger. The RAM may contain an outdated copy of the port E data because this can change and this communication may not occur in the next read. Therefore, what we do is we apply a qualifier known as the volatile to avoid the situation. In order to avoid this danger, we declare a pointer to an unsigned 32-bit integer which is volatile. So we are really making this number a pointer to 32-bit volatile integer. What do we mean by a volatile integer? Let's look at that. So a volatile integer is the one whose value can be changed by external means, even if the value is not changed within the program. So as an example, in case of our port E data, it is possible that our code does not change data on port E, but there's a sensor that is changing. Sensor has changed its output, and the output that is connected, the output bit is available at port E, that has been changed. So this volatile means that contents of the address, what is the address? Hex 4002434C can be externally modified. And not just by the program. And what are the means of external modification? The sensor. In our case, these are the traffic sensors. Therefore, whenever there's a danger that the contents of the RAM, in our case, because the ports are memory mapped, these are mapped to the RAM, the data on the ports can change by external means. Therefore, it is very important that whenever we make a reference to port E, the processor should get the updated value and not just the value from the RAM for performance improvement. That's not allowed. Whenever we reference port E, it means we read data. We read the fresh data. So we are reading, always read fresh data from port E. And also we store a copy of that data in the RAM but because we have a pointer to the volatile integer, therefore whenever we read the value of that volatile integer, it is always read from the source. So this volatile makes it possible to read value of the or just say read value from the source, which eliminates the hazard of reading in the stale data. And that's where, when we work with the ports, GPIO ports, where we have connected sensors, and sensors can update their values externally, and before we and it is possible that we may not recognize that. So whenever we read the port data, always declare a pointer to a volatile 32-bit integer. All right, so now we are ready to write our main C program, void main void. The program works with two variables: the current state CS, it is actually representing the index of the current state 0, 1, 2, 3, and the input, again there can be only 4 inputs, so 0, 1, 2, 3. It's remember, the input was coming in from the sensor. There was a 2-bit input, so 4 numbers. So we start with we start by assigning the current state. We start by assigning GoN to the current state. This is our initial state, or the start state, initial state. And then we enter an infinite loop. Whenever we want our microcontroller to keep performing or keep executing what is inside the loop and never to exit, unless of course we want to hand over the control to some operating system that we may be interested in. But in this case, the microcontroller we should like to keep our microcontroller busy in the infinite loop, is while one, which means that the traffic light control system will run forever. So let me put a comment over here: the traffic light system will run forever. All right, then we know the light corresponds to the data register of port B, and what we're going to do is that we are going to assign to the data register of port B the FSM index CS dot out, meaning the output of the current state. In each iteration, the very first step is to send the output of the current state. Where are we going to where do we want to send this output? Send output to port B. Or you can say port B data register to be more technically correct, but we'll just say port B because the lights are connected to port B. Then we invoke a routine whose input is the wait time. How do we access the wait time? The wait time is in the state description, the description defined by the struct. Remember, CS FSM was of type, the type of FSM was the state, and the second variable of the state was the time, the wait time. So essentially we are saying that go to the state, go to the current state and fetch the time, and then invoke a routine. This is the routine. Let me erase some stuff over here to make it a bit tidy. All right, so this is the routine. If you remember, we developed this routine in the assembly language. We can also discuss how to write this routine in the C language, but that remains part of our Q&A in the weekly Q&A. So for the moment, you can assume that there's a routine written in C that is called, and that is going to introduce some delay depending upon the delay specified by the current state. So once the delay has been introduced, our next task is to read data from the sensor. Input equals to sensor. So what is sensor here? So remember, sensor corresponds to the port E, the data on port E. Essentially, we are interested in reading the two least significant bits of port E. So the input is now input has been assigned sensor, which is the port E data register. So now we have read in the fresh. So this is the point. This is where this volatile really comes in handy. We'll read, maybe I should say read sensor, the fresh value of the sensor, because we declared sensors and light to be volatile. And then once the input has been read, then we have to now make a decision regarding the transition. What is going to be our next state? So the state struct has a third attribute, the variable that was given in the form of an array, next. And depending upon the value of the input, might it be 0 or 1 or 2 or 3, this is going to give us next square brackets input is going to give us the next state. It is going to tell us the next state. So CS has been set equals to next state depending upon the current state and the input once we have waited for the specified amount of time. This C program is much cleaner and it is much simpler than the corresponding assembly language program. However, there is always a trade-off between the simplicity of the code as far as the high-level language is concerned. There's a trade-off, the simplicity of the code and the corresponding assembly language code. So in this case, we don't know exactly what is the corresponding assembly language code when this C code is compiled. But as far as the ease of programming is concerned, this highlights an example where it tells us that it is fairly easy to implement a finite state machine engine in C. One thing that we haven't described in this program is the initialization of the timer and the ports. In fact, this is something that we shall discuss in our Q&A session. The slide is available in the lecture, but there will be no narration. So if you want to go through the slide, you can do it by yourself, but we can discuss that in the Q&A session. But the initialization of the port and timer is something that we are going to assume in every C program, and we are not going to make that as part of our main program as given here. We can define a similar data type, state, declared as structure, constant structure, containing those variables representing the output, the wait time. But then the third one is different. This is an array of pointer rather than array of numbers, as was the case in the previous example. In other words, next is an array containing 4 pointers. Each pointer value is an address of data type state, which cannot be modified or changed, therefore declared constant. So you can relate this constant with the fact that the state to which the pointer is pointing cannot change, hence constant, once initialized. Therefore, in this example, we are going to show you how you can use pointers to build the data structure and implement the state machine. So in order to initialize the states, we have 4 states. So this 4 represents 4 states. So we are declaring a finite state machine, FSM, of type state, which is defined here. And there are 4 states in the finite state machine of the type state. And these are initialized in the following lines. And these are going to be the elements of an array. The first element corresponds to the first row of the state machine table that corresponds to go north. The next one is weight north, go E, and the last row corresponds to weight E state. Now the important thing to note over here is that the output and the time attributes are the same as before, but the difference in this case is the implementation of the third attribute. In this case, this is a pointer. It is an array of pointers. Once again, it is important to emphasize that the third attribute of the state is an array of pointers. And each pointer is going to point. So array of pointers. So what should be the value of the pointer? So the question is, what does the pointer contain? The pointer always contains address. It always contains addresses. Therefore, this whole array is representing the next variable of goN, and the next variable is an array. It contains 4 pointers. Essentially, these are 4 addresses. These are 4 addresses. So the main difference over here is that goN, weight N, goN, weight N, go E, weight E, all of these are now going to be addresses. Therefore, we need to initialize these names or these variables, which are not going to be changed, by the way. So goN define, we're going to define goN by the address of FSM 0. So this is kind of an implementation of a linked list data structure. So FSM 0 is this guy over here, FSM 0. So this is an address. So goN is what? It is an address. So remember, delta represents an address operator. It is going to give us the address. So when we talk about delta FSM 0, basically we are talking about the address. It tells about address of FSM 0. The first the address of the FSM element at index number 0. It is an address. So because of this delta operator, and all of these states, goN, weight N, go E, weight E, these are representing some address, not the number. So in previous case, they were representing numbers 0, 1, 2, 3. It might be worth comparing with the previous slide. The second is weight N state, which is FSM 1. Third is the go E state, which is FSM 2. And the last one is the weight E state, which is FSM 3. Now, in order to understand this further, we're going to look at the pictorial representation, how this data is stored in the ROM. It may be helpful to visualize how the finite state machine data is stored in the microprocessor ROM. So we start with the goN state. So here we are representing the state. corresponding to the go north traffic. And this state was defined as a data type containing the output variable and the time, and then the third variable was the next, which was actually an array. So the out variable was a simple variable, scalar, time also scalar, but the next was an array containing 4 elements, and each element is a pointer. So the important thing to note over here is that goN, waitN are both the pointers. And pointers, the value of the pointer is always an address. Therefore, going back, referring to the previous slide, what is the value of goN? It is an address of FSM 0. So in other words, FSM 0 represents the goN, the state goN. FSM 0 represents state goN, whose address, when you put this delta operator, whose address is recorded in goN. So this goN variable itself is storing an address. So goN value is now an address. This is the important lesson, the takeaway of this slide. And the same goes for the go east. The go east state has the following values of its variables and attributes, and it is at finite state machine array index number 2. And go e, in this case we can say go e value is now an address. Similarly, wait n also represents an address. Wait e also represents an address. So address of what? So go e value we said was an address. It is an address corresponding to this state, and that's why it is shown here. So go, we can take a look at another example. Wait n value is now an address. What address? Think about it. What address? Wait n. We're talking about this address. Therefore, we can reference the wait n state components. Likewise, if we say wait e, what is the value of wait e? It's shown written here over here. It is an address. It was initialized representing an address. Address of what? This part, the wait e state. More specifically, it is pointing to the starting address. So as shown here, all these addresses are representing the starting address. But unlike the semi-language code, we are not going to add offsets. In fact, this is where the beauty of C language pointer lies, as we shall see in the next slide. No need for the offset. We can just work with the base. So all of these addresses are the base addresses. And that's where the pointers are so helpful. So without using offset, all we need is to work with the one type of addresses. Those are the base addresses. And if should we have to refer to any component of the state which is not at the base address, such as here, then we can make use of a dereferencing of a pointer technique, and we can have an access to any element or any component of the state, as we shall see in the next slide. So the good news is that in C we don't need to calculate offset addresses to reference elements of array or the variables of data types. Now let us move on to the C program for the implementation of the FSM. In our main program, we define a pointer PT of data type state, which was defined in the previous slide. So it is actually PT is actually a pointer, as shown here by the arrow. It is pointing to a data type that we call state, and we show what the elements, what the variables and the components of the states. And we would also like to work with another variable, but that's not a pointer, that is just a normal variable. It's an 32-bit unsigned integer input describing the input, which is fairly obvious. So once those are defined, then again, I would like to skip the code that is responsible for initializing the ports and the timer, as well as their configuration. That will be covered later in our Q&A session. Assuming that is done, then we're going to initialize our pointer. And remember, this GoN is an address. It is not a state. It is an address of GoN state. It is an address. So once the pointer is initialized, then we know what is at that address. We saw that in the previous slide. And these are the components of GoN state. So this is your GoN state, Go North state components. Its output is 21. Time delay is represented by number 3000, and then we have that wait next part. Sorry, that's a next. The last 4 elements are the elements of the next array. Then we enter an infinite loop as before, and now we are going to produce an output. This command light equals to pointer arrow out is interesting because we are going to send some data to the light, which is your, remember, this is same as port B data register. So reminder, light means port B data register. So what are we going to send to that port B data register? Well, we're going to see what is the value, what is the output of the state. Now we don't have the state variable, but we have a pointer to the state. So this is important to understand here. PT is a pointer to the state. It is a pointer to the state. So in order to retrieve the value out, in order to have an access, if we want to have an access to the output stored over here, then what we would like to do is to apply the dereferencing to the pointer. So you would like to dereference the pointer, and then this will actually be changing this arrow to an equals to sign. The way to think about it is that once you apply the dereferencing operator to the pointer PT, it is equal to this state, and then you can easily say out. And over here, this PT arrow out is the same. These two are the same commands. It is the same or equivalent. So either you do this PT steric bracket and then out, or you can just say PT out. Those are the same. So once that is done, we have obtained the output corresponding to the current state, and we have sent that output to the light, that is port B. And then we are going to, in the same way, we're going to retrieve the time variable of the data type state, and we're going to put that as an argument to the routine sysdig wait 10 milliseconds, assuming that routine has already been implemented somewhere. And we saw the implementation in the assembly. We can also discuss that implementation in C in the Q&A session. And then comes the sensor, which is reading in the values available at port E, that sensor. Here we are using simple variables, so sensor is just the input. So we just read the sensor value. And then finally, what we are going to do is to make a preparation for the transition. And for that, we are going to shift our focus on the last 4 elements of the state. Again, those last 4 elements are the next. The array containing 4 pointers. So in order to have an access to the next again PD arrow next, and which element do we want to refer to, that is specified by the input. So if, for example, input is 0, we are going to get GoN, and we are going to put PT equals to GoN. So essentially in that case, PT is equal to GoN. However, if the input was 1, then PT is set equal to weight N. And this is how it goes on and on. Once the pointer has been updated, then we go back and iterate over the loop. In fact, we are going to reiterate, and this process will continue forever. Our next problem requires us to implement a finite state machine for adjusting the duty cycle of an LED waveform. So we're assuming that the LED is connected to one of the port pins of the microcontroller, and it is turning on and off the LED. We can start with the 90% duty cycle, and we would like to have a state machine whose input is obtained from the switch, so that each time a switch is pressed, then the duty cycle changes. If we start with the 90% duty cycle, the next time switch is pressed, we go back to 10. Another switch input go to 30%, 50%, and then from 50 to 70 and 90, and this step and this continues forever. So as far as the implementation is concerned, we have to first think about the appropriate finite state machine for this problem. So the first question is, what are the states, what are the appropriate states that we can define for the system? What are the states? Well, the state can be LED on or LED off. And on corresponds to logic high and off corresponds to logic 0. So we have a state 0 or low, and we have a state 1 or high. So LED is on, so this corresponds to high state, and this corresponds to low. Or you can work with 1 and 0. All right, so with that in mind, we can have an on state and off state, but we're going to have, we would like to work with multiple 0 and 1 state, as I can show here. So initially with 90% duty cycle, when the duty cycle is 90%, then we know that when the LED, if the LED has just turned on, and assuming that the total time period is one thing that it is not mentioned here, but the time period is 500 milliseconds. That is 2 blinks. That is, well, actually 2 cycles per second frequency. So the time period is 500 milliseconds. Then if the LED has been turned on and it stays in a 90% duty cycle state, then the LED will remain on for 450 milliseconds. So once in the on state, this is actually the wait time. LED will remain on, and after that we go to the low state, in which the LED is turned off. So here the LED is off, and here the LED is on, and once turned off, it will stay off for 50 milliseconds, and then we go back to the on state. So this is from on to off and back from off to on. This continues forever unless there is an input from the external switch, which we haven't yet incorporated. Nevertheless, this is only applicable, these two states are only applicable for the 90% duty cycle. But what if we wish to go from 90 to 10% duty cycle, or let's say some other 70? So we had defined like 90%, then there was this 10%. So in 10%, the LED in the on state wait for 50 milliseconds and then goes to the off state, remains in that state for 450 milliseconds. So this the last pair of state corresponds to 10% duty cycle. This one corresponds to the 70% duty cycle. This is 50% and this is 30%. So we have a couple of states on and off for each value of the duty cycle. The question is, how can we connect? How can we go from one pair of states to another? Let's say from 90 to 10% or from 10 to 30%. How can we transition from one pair of states to another? Quite naturally, the change or the transition from one pair of states to another can be brought about by adding another state which corresponds to the switch input. In fact, this state is acting like a transition state. That's why the name is change 0. So what happens is that we have labels on the arcs that we did not discuss in the previous slides, but because there was no need for labels, but in this case they are very important. These are the inputs: switch input, and more specifically we say that when the input is 0 means that switch not pressed, and 1 means switch pressed. So 1 means switch pressed and 0 means switch not pressed. So these 1 and 0s are indicated on the arcs as an input. In the previous discussion we had 0. There was no role of switch. So once a LED is turning on and off with some duty cycle, it remains in that same duty cycle paradigm without any change. But now we want to bring a change, and that happens whenever in either low or high state corresponding to a duty cycle we have a switch input, that is switch is pressed 1. We immediately transfer well, after waiting for the time, if the switch is pressed and the information is latched, then we transfer to a new state over here, that's change 0. And as long as the switch remains pressed, once in that state we are going to wait for 50 milliseconds. This is again the wait time, and if the switch is still pressed we remain in that state. But if the switch goes back to 0, so it's like a switch which is turned on momentarily, allowing us to transition from one pair of states to another. Like we go from 90 to 70% duty cycle, we want to make this transition. Then this transition is brought about by pressing a switch and then release. So here the switch is released. We say switch not pressed, or we can also say switch has been released. It's like a push button. The best way to think about the switch in this case is a push button. So the switch pressed, we go from 90% duty cycle states to the transition state, stay in there for 50 milliseconds, and then when the switch was released we are ready to move on to the next pair of states, as is the case here. And this pair represents the 70% duty cycle. Then to go from the state to the 50% duty cycle states, we add a transition state over here that is again reached whenever the switch is pressed. So this again corresponds to the switch pressed. And if the switch remains pressed for more than 50 milliseconds, we stay in that state. But the moment switch is released, we make a transition to the next pair of states, which corresponds to the 50% duty cycle over here. So these two states in the middle are representing a 50% duty cycle waveform, 50%. And progressing this way, we can complete our finite state machine by adding these transition states, change 1, change 0, change 1, change 2, change 3, and change 4, allowing us to go from 90% duty cycle to 70% through this route, and then from 70% to 50% through this route, from 50% to 30% to this route, and from 30% to 10% duty cycle with with this route over here. And then to go from 10% to 90%, we're going to follow this route all the way up here. Again, depending upon whether the switch has been pressed and released afterwards. Your homework exercise will require you to write a C program for encoding the finite state machine for the LED duty cycle adjustment problem. And by encoding, I mean how would you place the data regarding the finite state machine, such as the output, wait time, and the transition to the neighboring states. And once you have encoded, you may wish to modify that finite state machine problem so that it can be used with the following program, which is very similar to the one that we developed for the traffic light signaling problem. But in this case, it will run the state machine for the LED duty cycle problem. With that, I would like to conclude a lengthy lecture. I hope you enjoyed listening to this lecture, and you may have some questions in your mind. For that, we are going to have our regular Q&A session on Thursday afternoon. But before I sign off, I would like to give slides credit to Jonathan Volveno. These slides have been taken and modified and tailored to the needs of our Mechatronics Embedded System course. Thank you very much and have a nice day.